Hi, my name is Alan Tu, and I'll present my doctoral research on selective computation for reliable and scalable vision systems. This work was selected for the Doctoral Consortium at the 20th IEEE International Conference on Automatic Face and Gesture Recognition, or FG 2026. First, a little bit about me. I'm currently a second-year computer science PhD student at the University of Maryland, College Park. My advisor is Professor Tom Goldstein, and I frequently collaborate with Professors Matthias Wicker, Vishal M. Patel, and Rama Chalapa. I previously interned at STR, and I will be joining Amazon as an applied science intern this summer. My research lies in the intersection of artificial intelligence, computer vision, and graphics, with publications in 3D and 4D reconstruction, biometric recognition, and generative modeling. My work is supported by two IARPA research programs. The first one is the walkthrough rendering from images of varying altitude, or WRIVA program, which I work on as a graduate research assistant at the University of Maryland. It focuses on unconstrained 3D reconstruction and novel view synthesis in challenging environments. The second is biometric recognition and identification at altitude and range, or BRIAR, which I worked on as a computer vision research intern at Systems of Technology Research, or STR. It focused on multimodal fusion of incomplete face, body, and gait recognition in severe operational conditions. In these two programs, I heavily collaborate with many universities to develop robust and scalable vision systems, and a lot of the publications that I'll talk about today are integrated into them. Now, I will introduce my dissertation research. Throughout my research experience so far, I have observed a reliable perception emerges when computation, data, and modeling capacity are selectively applied where they improve performance. Instead of treating them as competing objectives, my PhD dissertation research studies selective computation as a unifying principle for efficiency and robustness. It breaks this into three decisions. The first is what to compute. My CVPR 2025 and 2026 papers on 3D and dynamic Gaussian splatting approach this topic from an efficiency angle. The second is what to trust. In addition to my FG 2026 paper on face image recognizability assessment, which I will present during oral session 1 tomorrow, I am co-organizing the SPAR 3D workshop at CVPR 2026 in June. The third is where to generate. This direction is examined by my CVPR 2026 paper on incorporating generative priors into 3D reconstruction pipelines, as well as a recent paper on image condition CAD model generation that is currently under review. Although I split this presentation into categories, you'll notice that each paper explores more than one of these three decisions. First, I'll give an overview of my research on what to compute. For some background, 3D Gaussian splatting, or 3DGS, represents scenes as millions of differentiable Gaussian primitives with shape, position, view-dependent color, and opacity parameters. During training, Gaussians are cloned, split, and optimized to produce a photorealistic 3D reconstruction of the input images. The first work I will present, PUP3DGS, Principled Uncertainty Pruning for 3D Gaussian Splatting, was published at CVPR 2025. I was a co-first author. For each of the works I will present today, the full manuscript, open source code, and interactive video results can be found at the featured website. The research that became PUP3DGS actually started as a what to trust paper instead of what to compute. We wanted to measure uncertainty in 3D Gaussian splatting models. In the figure on the left, a small Gaussian as close to the camera and a big one far away from the camera appear the same once projected to the image plane. Since we only have one viewpoint, the 3DGS model is under-constrained and we are uncertain where to place the Gaussian. In the figure on the right, we have multiple cameras. Since we optimize it to reconstruct every view, the 3DGS model is now well constrained and we are certain where to place the Gaussian. Previous papers measured per Gaussian uncertainty by examining the loss basin of the L2 reconstruction error. However, I wasn't convinced by this model of uncertainty because my own analysis showed that it doesn't actually capture error. In fact, it is outperformed by random selection in their own published setting of next best view selection. I reinterpreted this uncertainty as per Gaussian sensitivity. If the loss basin is wide, then we can perturb the Gaussian parameters a lot without changing the rendered image. If it is narrow, then even perturbing it a little will change the rendered image. A way to examine this per Gaussian sensitivity is through the Hessian of the L2 reconstruction error. However, this is expensive, so we compute the Fisher approximation instead. Note that this is exact when the models converged. in that it does not rely on any ground truth information, so it can be used during inference as well. We compute the sum of this Fisher approximation for each view in a training set to capture each Gaussian's cumulative sensitivity across the entire scene. Then, we take its log determinant to turn it into a scalar sensitivity score. Sort the Gaussians by their sensitivity scores. If a Gaussian has low sensitivity, then it means perturbing its parameters changes a rendered 3DGS model only a little or not at all, implying that it is either redundant or not visible at all. Thus, we use a sensitivity score to print a large percentage of the Gaussians in the model, then fine-tune it on the training set to recover any degradation. In the paper, PUP3DGS takes a trained 3DGS model and does 2 stages of this prune-refine process. We find that PUP3DGS can prune 90% of Gaussians from any pre-trained 3DGS model, achieving 3.56 times faster rendering speed while preserving visual quality. This was groundbreaking at the time because it implied that 90% of Gaussians and vanilla 3D Gaussian splatting are essentially redundant or useless. In addition to pruning significantly more produce than previous methods, PUP3DGS's sensitivity-based pruning also retains more fine detail and salient foreground information. You can see that light Gaussian fails to reconstruct details like the text on books, while PUP3DGS preserves them. Subsequent papers, including the next 2 that I'll cover, also conclude that 3DGS can have a little over 10 times fewer primitives at most before substantial visual degradation. PUP3DGS is now a standard citation in 3DGS densification and compression literature. The second CVPR 2025 paper that I'll cover is Speedy Splat, fast 3D Gaussian splatting with sparse pixels and sparse primitives. Our full paper and GitHub repository are also available on the featured website. Speedy Splat aims to accelerate 3DGS rendering speed by as much as possible. We find that rendering speed is primarily limited by 2 factors, the number of Gaussians allocated to each pixel and the total number of Gaussians in the scene. Our localization algorithms reduce the number of Gaussians allocated to each pixel by the rasterizer. 3D Gaussian splatting uses a conservative heuristic that draws a large bounding box around the projected Gaussian, grossly overestimating its actual tile extent. Our snugbox algorithm draws a tight bounding box around the Gaussian. Then, our accutile algorithm uses it to compute the exact tile intersections of the Gaussian. These accurate tile localization algorithms make rasterization much more efficient without altering the rendered image. We also reparameterize the PUP3DGS sensitivity pruning score, reducing its storage requirement by 36 times. This allows us to prune the scene during training. We periodically soft prune the scene at fixed intervals while the 3DGS model is densifying, as well as hard prune the scene after densification is completed. When Snugbox, accutile, and our end-to-end pruning pipeline are combined, Speedy Splat achieves 6.5 times faster rendering speed, a little over 10 times fewer primitives, and 45% faster training than original 3D Gaussian splatting. Furthermore, our Snugbox and accutile algorithms boost FPS by 2 times for free. Since they can easily be dropped into any 3DGS rasterization pipeline, our code appears line for line in many user-facing 3DGS platforms and recent academic publications. Speedy 3DGS, Speedy Deformable 3D Gaussian Splatting with temporal pruning and motion grouping will be featured at CVPR 2026. I am its first author. Dynamic Gaussian splatting methods extend 3D Gaussian splatting with deformations at each time step, allowing them to reconstruct monocular video. Motion models for these methods generally fall into 2 categories. Neuromotion is slow but produces high visual fidelity, while non-neuromotion is fast but produces lower visual fidelity. Speedy 3DGS aims to deliver the high fidelity of neuromotion models for dynamic Gaussian splatting at speeds substantially faster than non-neuromotion models. First, we extend the Speedy Splat end-to-end pruning pipeline to deformable Gaussian splatting. This involves careful analysis of the temporal domain and the effect of motion and inaccurate camera transforms on Gaussian densification. Our temporal sensitivity sampling method also adds a temporal perturbation to the timestamp input of the deformation network during sensitivity score computation. This perturbation reveals unstable primitives and floater artifacts that are visible between the timestamps in the training dataset. Speedy 3DGS's temporal pruning reduces the total number of Gaussians by over 90% while preserving visual fidelity and temporal coherence. Notice that temporal sensitivity sampling removes floaters that are visible in the baseline model. Given a dynamic Gaussian splatting model with learned motion, Our group flow method groups Gaussians by motion similarity, then learns a shared SE3 flow for each group. This distills a high fidelity but slow per Gaussian neural deformations into a much smaller set of efficient grouped SE3 transforms. When compared to the deformable GS baseline, speedy 3D GS achieves 11 times faster rendering speed and 59% faster training on the NERF DS dataset, as well as 29 times faster FPS and 73% faster training on the HyperNERF dataset. We also integrated into the monocular dynamic Gaussian splatting benchmark. Over 5 datasets and 50 scenes, speedy 3D GS achieves over 100 FPS faster rendering speeds and better visual fidelity than all non-neural baselines. Our second decision is what to trust. Transfer Learning for Face Image Recognizability Assessment is featured here at FG 2026. I will present it during Oral Session 1 tomorrow. Existing face image quality assessment, or FIQA methods, struggle in unconstrained real-world scenarios. In addition to being trained on generic face recognition datasets and evaluated on saturated benchmarks, their curated labels do not correlate with the cosine similarity used for feature matching, and they are coupled to the decision geometry of specific backbones and training objectives. We define and compute recognizability, or the likelihood that an image will be correctly identified, grounded in the decision geometry of the given encoder. Then, we append a single linear layer and fine-tune the entire network to regress the ground truth labels. This transfer learning approach adapts the encoder to predict recognizability from its own embedding geometry. Transfera achieves state-of-the-art image-level FIQA results. The gap is especially large on BRIAR Protocol 3.1, which is a proprietary video surveillance dataset that is out of distribution for general face recognition training datasets. We also introduce a recognizability-informed template aggregation strategy that uses the predicted recognizability labels to filter and weight templates. This emphasizes compact, reliable samples most representative of the correct class. Transfera's template aggregation strategy outperforms all previous FIQA methods. Notably, the verification performance of the open-source inside-face arc-face encoder on BRIAR Protocol 3.1 improves from 0.43 to 0.87 TAR at 10 to the negative 3 FMR, and from 0.08 to 0.60 TAR at 10 to the negative 6 FMR, even though the arc-face encoder itself was never pre-trained on any BRIAR or video surveillance data. Transfera also extends recognizability prediction beyond faces for the first time, establishing it as a unified framework for modeling recognizability across modalities. The appendix also explores this encoder-specific explainability signal, which extends to unseen subjects and provides avenues for safeguards, re-enrollment, and hard example mining. I'm also co-organizing the Sparse 3D workshop on security, privacy, and adversarial robustness in 3D generative vision models at CVPR 2026. We will feature papers on topics like threats and vulnerabilities in 3D AI, content ownership, secure generation and evaluation, and multimodality applications and societal impact. Find more details at sparse3d.org. Our third topic is when to generate. SplatSure, selective super resolution for multi-view consistent 3D Gaussian splatting, will also be presented at CVPR 2026. We observed that uniformly applying single image super resolution to low resolution 3D.js training images introduces multi-view inconsistencies that degrade visual quality and faithfulness to the ground truth. SplatSure introduces a geometry-aware strategy to selectively apply super resolution only in undersampled regions lacking high-frequency supervision. It produces sharper, more faithful reconstructions that better align with the ground truths than previous methods, while maintaining multi-view consistency. Notice that the baseline SRGS model produces blurry renderings, whereas ours successfully reconstructs fine detail. I also recently submitted a paper on image condition CAD model generation. It produces much higher quality and more reliable generations than previous methods and scales to highly complex objects, as well as out-of-distribution domains. Finally, I will discuss some of my ongoing research directions. They primarily explore how selective computation can make generative modeling in 3D and 4D reconstruction both efficient and robust. I am currently exploring how we can scale reference context for multi-view diffusion models to improve cross-view consistency. A relevant paper is SyncFix by my IARPA BRIAR colleagues at Johns Hopkins University. I am also currently developing diffusion priors for sparse view 3D reconstruction. Since diffusion models are prone to hallucinations that degrade downstream reconstruction quality, I am researching Splatcher-like uncertainty-aware methods for selectively incorporating generative priors. For my applied scientist internship at Amazon's last mile delivery org this summer, I will research reconstruction and generation methods for embodied AI in dynamic environments. Lastly, I am designing new representations for efficient, high fidelity, and capable 3D and 4D reconstruction. For example, I have worked with Voronoi-like representations based on a radiance film paper by Simon Fraser University. I'm Alan Tu, a computer science PhD student at the University of Maryland, College Park, and I presented my doctoral research on selective computation for reliable and scalable vision systems. You can find my CV and publications at 2allen.github.io or contact me at 821@umd.edu. I am open to any feedback on my completed and ongoing research, as well as potential collaborations. Thank you.